This next optimization problem that I've been sent seems fun. I've actually never seen this problem before, and so I'm even more excited to do it. So it says a wire of length 100 centimeters is cut into two pieces. So let me draw this wire. So that's our wire. And it's going to be cut into two pieces. Let me read the whole thing before I draw anything. One is bent to form a square, and the other is bent to form an equilateral triangle. Where should the cut be made if A, the sum of the two areas is to be a minimum or a maximum? And it says allow the possibility of no cut. Fascinating. So this is 100 centimeters long. Doesn't matter if it's centimeters or meters or whatever, right? So it's, it's 100 long. Could be 100 miles long. That's 100. And we're going to cut it at some point. We'll cut it there. And let's just, well, I shouldn't have done that because I was going to use x and y. But actually, let's use a and b since I made the cut look like an x. So let's say that is a centimeters from the left-hand side of the wire. And then what's the distance from the right-hand side of the wire? I could call it b, but even easier would just say, well, if this is a, then this is going to be 100 minus a. This is 100 minus a. And then they say, I'm going to take one of the wires, let me just say the left-hand wire, and I'm going to take it and I'm going to form a square, so not a rectangle, a square. And then the other wire is going to form an equilateral triangle. Okay, so let's do it. And actually, I can already sense that it will be easier to manipulate this one. So I'm going to make the equilateral triangle out of this side and make the square out of this side, just because I have a sense that it'll make the math a little easier. So I'm going to take this wire of length A and form an equilateral triangle out of it. Right? So what is the triangle going to look like? It's going to look like, and I'm going to arbitrarily switch colors now. So this is my equilateral triangle. All the sides are equal. And how long are each of the sides going to be? Well, the whole perimeter is A. So each of these have to be a over 3. A over 3, a over 3, and then a over 3, a over 3. And then I also have a square with the leftovers. And that has a, not that I was using the square tool. Since I have it, I should use it. So I have I don't want to do it like that. Okay. So there's my square. And if the whole perimeter is 100 minus a, what is the length of each side? It's going to be this divided by 4, right? Because all the sides are equal. So what's this length divided by 4? 100 divided by 8 by 4. 100 minus a divided by 4 is 25 minus a over 4, right? So this side is 25 minus a over 4. This side is 25 minus a over 4. And this is the same thing, 25 minus a over 4. And this is 25 minus a over 4. And they want us to find what value of a. They want to find, let's see, they say the sum of the two areas, right? They want to know what value of a minimizes. Is that my phone? No. They want to know what value of a minimizes the sum of the two areas and maximizes the sum of the two areas. So what are the sum of the two areas? What's the area of this triangle? I always forget the formula for the area of an equilateral triangle, so we'll have to kind of derive it right now. So what I do is I draw something like that, and then we know that this length right here is a over 6. That's a over 6, right? I'm just doing the halfway point. The whole thing is a over 3. And if this is a 30, 60, 90 triangle, right? That's 30. This is 60. So this is going to be square root of 3 times this. So the height, let me do that here just so you know what I'm doing. This is just some geometry. I'm drawing half the triangle. This would be a over 6. That's a over 3. And so this would be square root. I want to make sure that I'm doing right. This is going to be the square root of 3 times this. So square root of 3 over 6 times a. So what's the area? Well, the area of this half triangle is base times height times 1/2. So the area of the whole triangle is just going to be this base times this height. So the area of the triangle is equal to this base times that height. So it's area area over 6, that's this, times the height, times square root of 3 over 6 area. And just so you remember, area of a triangle is 1/2 base times height. So if we did 1/2 base times height, we would get the area of this triangle, right? But the area of the entire triangle is 2 of these triangles. And so that's why I got rid of the 1/2, because it's 2 times 1/2 base times height. So hopefully that doesn't confuse you. That's just a little bit of geometry. So anyway, the area of the triangle is equal to the square root of 3 over 36 a squared. And what's the area of the square? That's easier. That's just base times height. So area of the square is equal to 25 minus a over 4. That's just base times height squared. And that is equal to 625 minus 2 times, so it's 25 over 4 minus 50 over 4a, right, minus 50 over 4a, 50 over 4a, plus a squared over 16. So that's the area of the square. But we want to know the area of the combined area of both of them. So what's the function for the combined area? So the combined area, and I'll do it in a bold color, the area of both of them, I'll say area combined, that's equal to the area of the square plus the area of the triangle. So the area of the square is let's see, it's a squared over 16 minus 50 over 4a plus 625, and then we want to add the area of the triangle, plus square root of 3 over 36 a squared. And we could, that's as a function of a. We could put it like that. So now we have to optimize it, and we want to find the minimum point and the maximum point if they exist. Let me clear up some space. We've already, the area of the square is already implicitly there. I can actually clear up all of this here. And so what is the derivative? A prime, the combined, well, actually, hope you don't mind. I'm going to erase that too, because I think I'm going to run out of space and just get all bunched up otherwise. That's not what I wanted to do. But you know what we're talking about. We already have figured out the area of the combined entities. And so now it's just pure calculus. All the geometry is done. So what is the derivative of the combined areas as a function of a is equal to the derivative of this expression? So it's 2, so it's, what is this? 2 times 16, 2 over 16, so it's a over 8. So let me write this. Well, I'll try it as a over 8. A over 8. Let me draw a line here. I don't want things to get confused. A over 8 minus 50 over 4. This derivative of 625 is just 0. Plus 2 over square root of 3 over 18a, right? And so we want to find the minimum or the maximum values for this. So let's set this equation is equal to 0. So we get, let me see what we can do. Let's say we could add the a coefficients. So we have 1/8 plus square root of 3 over 18a, right? I just added that to that, minus 50 over 4. And we want to set this derivative equal to 0. So let me switch colors arbitrarily. And so we get, let me add these two fractions. So 8 and 18, what's their common denominator? So 8 and 9. 8 and 9 is, what is it? Is it 8 times 9? Is it 72? 72. And 1 over 8 is the same thing as 9 over 72. And so 18 goes into 72 4 times. So that's plus 4 square roots of 3. And all of that times a is equal to 50 over 4. And now we can multiply both sides times the reciprocal of this coefficient. And we get, this isn't as, maybe I made a careless mistake, but the numbers aren't coming out too clean, but maybe they're not meant to. A is equal to 50 over 4 times 72 over 9 plus 4 square roots of 3. And let's see if we can cancel anything out. This 4 becomes, this becomes an 18. And so we get A is equal to 50 times 18 divided by 9 plus 4 square roots of 3. Now let's see if that makes any kind of sense. And I think I'm going to have to get the calculator for this one. Calculator. Okay. So what should I do first? Let me figure out what the denominator's value is. So 3 square root times 4 equals plus 9 is equal to 15.928. So that A is equal to, what's 50 times 18? It's 50, 90, right? 5 times 8 is 40, right? So it's 900 over 15.928. So let me do that. So let me just invert that times 900. It equals 56.5. So A is equal to 56.5. So at least we got a number that makes sense. It would have been unfortunate if the point that we had to cut this wire was some number larger, or God forbid we had a negative number there. But we actually got a positive number, and it's a number between 0 and 100. So we are probably right. So, but the question is this a minimum value or is this a maximum value? And to figure that out, well, let's just see if we're concave upwards or downwards at this point. So let's think about it. So let's take the second derivative of our combined area function. So this was our combined area function. Right? We had set it equal to 0. So let's take the second derivative of that. Well, that just equals, the derivative of this, it equals 1/8 plus square root of 3 over 18. Well, times a, but so it's just a coefficient, and then that goes to 0. So that equals a prime prime as a function of a. The combined areas as a function of a. It's just a constant number, and it is a positive constant number. So what does that tell us? Given that that is a positive constant number, that tells us that at any value of a, the second derivative is positive. The second derivative is positive tells us that we are concave upwards, really over the whole function, this whole combined area function. We're concave upwards and concave upward. And how do we know that? Well, if the second derivative is positive, the slope is always increasing, right? And that tells us that any value where the slope is 0, which was this one, is actually a minimum point. So A is equal to 56.5. So if we cut it at 56.5, we are actually at a minimum point. So how would we maximize the combined values? Well, maybe here we have to just take one of the boundary conditions. So maybe we could set A is equal to 0, or we could set A is equal to 100 and figure out what the values are. And one of those have to be our maximum value. So what happens when A is equal to 0? So so this was our function to begin with. What is our combined area function if A is 0? Well, this is 0, this is 0, that is 0, so it equals 625. 625. And what is that? What does that translate into? That's the case where the entire wire is used to make a square and none of the wire is used to make a triangle. In that situation, our combined area, and all the areas coming from the square, would be 625. Well, what happens when A is equal to 100? when a is equal to 100, when a is equal to 100, well then all of the if this is equal to 100, then the square, the area of the square is 0, so we can actually even ignore these terms. We actually know that this will evaluate to 0 because we are committing no wire to the square. And so what is the area of the triangle? Well, this term right here was the area of the triangle. So it equaled square root of 3 over 36 times 100 squared. So what is that? So let's see if we can do that. So 3 square root divided by 36 is equal to, and then 100 squared is 10,000, right? So times 10, 1, 2, 3, 481. Go 481. So what do we know? We know that if we cut it exactly at 56.5, and it's actually there's a little bit more precision that I kind of didn't pay attention to. But if we cut it at roughly 56.5, the combined area, actually we haven't even figured out what that combined area is, but we know it's a minimum point because we're concave upward at that point. And as a fun exercise for you, you might want to plug it into your calculator and figure out what the actual area is at that point and realize that it is the low point. So that is the minimum value. That's how we minimize the area of the square and the triangle. Now, if we committed all the wire to the square, we get an area of 625, and all of it comes to the square. If we cut it so that we cut it here, so all of the wire is used to make the triangle, we get an area of 481. So the maximum value is when a is equal to 0, and our combined area is 625 because we're doing a square with the whole wire. And the minimum value is when we actually cut it right there at 56.5. So where we commit 56.5 to the triangle, and we commit, the remainder. So what is that? 43.5 to the square. That's when we minimize it. That was frankly a fascinating problem, and I hope I got the problem right. And even if I made a careless mistake, I think you understand how to do the problem. I will see you in the next video.